Hello and welcome to Cisco ACI Field Engineer Implementation, Application Modeling and Deployment, Module 6. This is a very short segment. We'll design an application profile, a quick RESTful API review. We'll do some initial brush on network programmability and the ACI toolkit. Designing an application profile. What you need to do is review your application flow. You do have to get agreement from specific applications, on how your applications actually work. We want to be able to identify EPGs and contracts. So when we identify an EPG is when a specific group gets the same services from the network, or if there are no network services between the groups, we can actually view that as devices in each group are free to communicate with each other. So an EPG should basically be a presentation tier, a mid-range or Unix system. And in this case, this is an application to retrieve an MRI image from a patient care system. So of course there would be images, any authentication for the EPG. So basically, if we request an image from the presentation tier on the virtual machine, we're of course authenticated. And then we need to take a look at our network services. Do we have a firewall or a load balancer to go to multiple application tiers? The application tier itself will then communicate via contract to the image indexing and storage tier, and then provide that information back. So you can see here the length from the time the image is requested to the image is actually received. It does go through several points which are actually defined in the application profile. So here's another example under the tenant Cisco Health. So network services are provided as service graphs called by the contracts between the EPGs. So you can actually view that the contract between the web and app tier and the contract between the app and the actual database tier have firewall inspection and have load balancers as well. So those are provided as service graphs, which are then integrated with the contracts to allow for that traffic to flow between those endpoints. RESTful API review. So again, this is a Apex and Open API and open source. So the REST API overview. REST, first of all, stands for Representational State Transfer. So it's used by browsers, can be thought of as the language of the internet. Now the cloud usage is on the rise. Various application programming interfaces are emerging to expose web services, and REST is a logical choice for building APIs that allow end users to connect and interact with cloud services. A RESTful API is an application programming interface that uses HTTP requests to get, put, post, and delete data. RESTful APIs typically take advantage of HTTP methodologies defined by RFC 2616 protocol. They simply use put to change the state of or update a resource, which can be an object, file, or block, get to retrieve a resource, post to create that resource, and delete to remove it. So you can actually take a look. Everything is represented as an object, and every object could be manipulated via REST. It's supported REST operations we've already talked about, support for JSON and XML. So what you need is the HTTP or HTTPS protocol, the APIC host and port, the API operator, which is always going to be in the API folder. Then you're going to have the managed object or class operator, the distinguished name or object class, encoding for the response, either XML or JSON, and then any specific options, filters, selectors, or modifiers. So here's to create a REST in XML or a REST in JSON. Here's your HTTP method. Here's your request URL. Now the request URL you can find in any specific in the actual API by very quickly looking at the API Explorer. So you can do that. There's also examples on a GitHub as well. So you can do creating a tenant very easily with Postman. You can create an application profile. So there's your method to post, the request URL, and the payload. So you can see the payload for XML is a lot easier than the payload for JSON. That's my opinion, but there's just less work to do in XML than JSON. So when you're learning about network programmability, It's not the easiest thing in the world to pick up, but but if you learn to do simple tasks, generally playing with the ACI inspector and then taking that code and URL and payload, popping in the Postman does make things very easy. This is a journey, so you need to be able to crawl, walk, and then run. Here's some network programmability resources that you can use to continue to extend your knowledge on programmability. The ACI toolkit is a simple toolkit built on top of the APIC API. So there's a set of simple Python classes. There's a Python library. You can use that to generate REST API calls. It runs locally. It's not full functionality. It's just the most common sets, and it's focused primarily on configuration. So basically, it preserves the ACI basic concepts of tenants, EPGs, contracts, and etc. And you can actually pull that from GitHub. So if we actually take a look at the ACI toolkit, the idea is to make the scripts that are easy to develop and read as well. So here we've commented out specific information: create the tenant, create the application profile, create the EPGs, create a context and bridge domain, and then we've actually added the code. So what you can do is that the variable becomes an object once the function app profile has been created from the application profile my demo app. So the next two variables, web EPG and database EPG, become objects once the EPG function created the web front-end EPG and the database back-end EPG. Context variable becomes an object after the context function creates VRF1 under the ACI Toolkit demo tenant. So you can actually run through and add additional stuff, and you can play, and it's actually a lot of fun. ACI Toolkit applications, here's some additional ones. Connection Search is a standalone web app that runs on the local host and connects to the APIC via the RESTful API. It can produce a database of endpoint connectivity. Event feeds convert ACI events to Atom feeds. Atom feeds are used by some NOC and NMS solution. Cable plan application is a tool to create and compare cabling of an ACI fabric. And then ACI reports is a collection of reports around security, physical switches, and logical. Fake APIC, the fake APIC is designed for users to view managed objects and their properties based on the JSON configuration files. And here's your prerequisites for running the ACI toolkit. We will go ahead and continue, since that was a very short segment, we will go ahead and continue the Cisco ACI field implementation, hypervisor integration. We're going to spend more time on VMware as opposed to Opflex or Microsoft or containers. We'll actually show those slides, but we're not going to do a whole lot of actual dialogue on those specific slides. But the information is there depending upon the specific use case. So, virtualization primer, I'm just going to go very quickly. Bare metal servers, virtualized servers. You can run multiple operating systems, abstracts the hardware that's actually running on a physical server. Allows us to run multiple operating systems as virtual machines, thereby utilizing our servers a lot more efficiently, as well as RAM and CPU. And allows for grouping of servers for any sort of failover situations. Distributed virtual switches actually allow for a large bridge domain to exist that's expanded over multiple servers. And as you can see, you can move virtual machines over between hosts. I'm not going to spend a lot of time on that. From an ACI perspective, the policy coordination with virtual multiple machine managers, ACI can connect to VMware, System Center, KVM, as well as containers and other hypervisor components as well, and or Docker as well. So from a VLAN specific, if you have port local VLAN enabled, current hardware, the leaf switch supports 10,000 per logical port. Hardware has 16,000 entries of port VLAN table that's used to map the incoming traffic to an internal VLAN and in turn map to an EPG. So effective supported entries is up to 10,000 due to hash collision. No such port or VLAN limitation from hardware with default mode. Current testing and support for logical port scale from a software's perspective is 64K per leaf, with bridge domain scalability remains the same with the port local VLAN. So your port local VLAN applies VLAN significance at the port level, allows reusing the same VLAN space on a leaf. Combination and port is used to identify incoming packet and map to an EPG, and it allows hosting providers to sell ports and allow customers to bring their own VLAN space. If you do enable that, then the VLAN requires separate VLAN namespace when sharing on a top of rack switch. So when you disable port local scope, then you can reuse multiple vCenters with multiple VLAN namespaces on the same top of rack switch. As you can see, vCenter 1 and vCenter 2, they do not have overlapping pools, so you can use that VLAN namespace on either top of rack switch. But as you can see here, it's not allowed to have the same overlapping unless you enable port local scope. VLAN significance, EPGs do not really care about VLAN numbers. They care about pools. EPGs don't care about IP addresses. EPGs can take a different network identity across VMM domains. They can span multiple VMM domains. So in this case, ACI abstracts the connectivity policy of forwarding aspects, allows EPGs to take different network identities across multiple VMM domains. Allows the same application to be deployed in different VMM domains. VM mobility is prohibited between VMM domains that are not compatible, right? You're not gonna vMotion between vCenter and KVM, and vMotion between vCenter domains is prohibited prior to vSphere 6 anyway. But it's understand that VMM domains, VLAN tags, and the IP addresses and the VLAN tags that are tied to the port group in vCenter do not matter anymore. So we'll talk more about that shortly. So VMM applies the network configuration by placement of VNICs into port groups in VMware, VM networks in Hyper-V, networks in OpenStack. EPGs are exposed to the VMM as a one-to-one mapping to the port groups. So just like you would run any single port group. So if you actually take a look, the application profile has our three-tier app, firewall, load balancer, and EPGs. So how does the ACI fabric? It assigns an endpoint to an endpoint group. What are the endpoints in a virtual environment? They're the VM VNICs. How does VMware apply network configuration via port groups? Those port groups will have a VLAN tag, but that VLAN tag will have it will not be 172.16.40 on VLAN 40. It will be a pool of VLAN tags, because remember, the VLAN is locally significant inside the fabric, but it has no tie-in to the actual endpoint group. The EPGs are exposed to VMware as distributed virtual switch port groups. So all we do is we establish a management connection to vCenter, and then we copy the port group down. So ACI, how does ACI find or discover virtual endpoints? So there's two options. There's a control plane, there's an OOB handshake, or an in-band via OpFlex, and or in Microsoft 2012 vSwitch does that differently. Via control plane or via the data path. So control plane learning is an out-of-band handshake with vCenter APIs. There's an in-band handshake where OpFlex enabled or the host via LLDP or CDP. Okay, so we all know that the ACI fabric runs LLDP. You can also enable CDP and have that. Data path learning is distributed switch learning. LLDP is used to resolve the virtual host ID to the attached port on a leaf node for non-OpFlex hosts. And the in-band handshake for LLDP and CDP is for OpFlex-enabled hosts. So endpoint identification can be a physical endpoint defined in the APIC, switch interface in VLAN, leaf node, bare metal server, or a virtual endpoint where we make a connection to vCenter and EPG. Port group gets created and copied down. EPG is then tied or the virtual machine is tied to the port group, and the EPG is tied to the VMM domain. So each EPG in ACI is rendered as a port group in vCenter. So here's the process for actually doing the VMM integration in vCenter. You'll create your application profile. Then you will go to virtual networking. You'll create your VMM domain, which of course you will establish your connectivity with vCenter. APIC will then create the distributed virtual switch in vCenter. Then in vCenter, you'll add your ESX host to the distributed virtual switch. You'll add and manage hosts. Then in the tenant, you will associate EPGs to the VMM domain. APIC will then create the port groups in vCenter, and then in vCenter, you'll assign port groups to the individual machines. Deployment discovery with hosts directly attached. The ESX host discovers the neighbors via LLDP, communicates this information to vCenter, which in turn provides it to the APIC. So if we actually take a look from a policy perspective, our AEP maps the VMM domain to the interface policy groups. What are the interface policy groups? The interface policy groups are each individual interface that host is connected to, and that's bound to the switch profile, which is the group of two switches. So on interface 10, LLDP is discovered, and he'll say, hey, look, I'm connected to leaf 101 port 10 and leaf 102 port 10. And the policy resolution is handled by the APIC. So there's not that very many people that run UCS-B series pre 2.2, but ACI uses LLDP. LLDP was supported northbound, but not supported between FI and ESX, only CDP. So there is a process in where you have to go and set a policy in UCS. So we'll do a leaf policy to enable LLDP and CDP, and then we'll configure CDP from the UCS host. Then we'll configure our network control policy, enable CDP, and go from there. So ensure CDP is enabled on the interfaces in pre 2.2. Not very many people run 2.2 anymore. Design considerations. Hosts are assigned a VLAN ID to EPG binding through VMM and APIC. Intermediate layer 2 nodes are not managed. They need to manage VLANs on these for each VMM domain. Endpoint location discovered through stitching, LLDP time to life on non-OpFlex enabled hosts. So on the APIC side, under virtual machine policies, we'll go through actually creating your VMM domain. Give it a name. You want it to be a distributed virtual switch. Type attachable entity profile. That's going to be very important. VLAN pool and vCenter admin credentials. And then vSwitch policies on APIC for UCS-B series. We do actually do route based on originating port ID because usually in UCS those are actually port channel connections. So what we want to do is the APIC's in charge of mapping the stitching of those links, so we do route based on originating port ID. vSwitch policies for UCS-B series. If we configure a MAC pinning policy, it programs the port groups to use this mechanism. It's very important in order to prevent packet loss. So the leaf would see UCS on ports X or Y for FI1234. ESX host also sees the same UCS on VMNIC 0 and VMNIC 1 for the FI with Ethernet Y and Z ports. When the VMs come online, vCenter informs the APIC. This comes up on whatever interface. The APIC associates the EPG policy from the port group to the ports on the leaf itself. So here we go to vSwitch policy, and that's where we're talking about the port channel policy, LLDP, and CDP. But as of 3.0, UCS supports LLDP anyway, so it's fine. So if you want to actually create a customized role for just a vCenter admin, you need to create a vCenter role with the following privileges. So an APIC administrator or Fabric administrator can actually log into vCenter and see the port groups copied down. So once that's done, you will actually see in the APIC, you'll see the new distributed virtual switch in the APIC, and then you'll see the new distributed virtual switch on vCenter. So here you will add that VMM domain association. Now, what are we talking about here? we are binding that EPG to that VMM domain. So then that becomes the port group. So OpFlex will go very quickly. It's an extensible policy resolution protocol designed for declarative management of any data center infrastructure. So the APIC uses the OpFlex agents. So that's how the APIC actually talks and distributes information throughout the fabric from a policy perspective. It's abstract rather than device specific. It's flexible using XML or JSON, and it'll support any device that actually that can actually talk OpFlex. As you can actually see here, here's the OpFlex protocol. I'll just let that sink in basically, but the policy element, when the endpoint attaches, the switch does an endpoint declaration and policy resolution. So that's what we were talking about yesterday. Pulls a subset logical model into the policy element. The policy element is from logical abstract form to concrete model. Lets the switch have control, but he has to honor the abstract policy. Policy element reports the status and faults to the observer, which is in the APIC. The endpoint registry knows where every device in the network is and is responsible for learning and knowing it. The policy repository receives information from a user and tells what user intent was from a policy perspective. So here's the OpFlex agent architecture. There's the Neutron OpFlex agent, receives updates from OpenStack about new endpoints. The OpFlex agent runs the OpFlex protocol with ACI leaf proxy, programs opens via switch via OpenFlow. The endpoint file is located in the varlib OpFlex agent OVS. Storage is for host local information. And the Open vSwitch are the policies pushed by OpFlex agents. The OpenFlow is implemented on the kernel data path. And there's additional references for OpFlex and ACI. So here we're going to start to go a little bit faster here. The Cisco ACI Virtual Edge is decoupled from the hypervisor kernel. It lives in user space because, as we know, with VMware as of 6.0, they closed off the kernel. So so you're not going to have in-kernel support. So this lives in user space. It's a VIB file that gets updated. So you've got the Cisco AVE, which is hypervisor agnostic, or the legacy AVS, which is hypervisor dependent. Both live in user space. The kernel still uses the native vSwitch, and under the kernel in the legacy AVS uses switching and policy enforcement. You're going to see more AVEs. As you can see, the AVE can reside in Red Hat and Hyper-V and ESXi, consistent feature set, VXLAN, microsegmentation, distributed firewall, independent operations and upgrades, no impact on the hypervisor. AVE is managed and configured by the APIC. So the AVE brings networking features widely used in the physical world into the hypervisor. Application profiles configured on the APIC are pushed to the AVE, and it utilizes the OpFlex protocol. So here's how you would actually deploy the AVE. It employs the ACI vCenter plugin, and you need to run the migration tool to upgrade from an AVS. But you'll deploy and upgrade the AVE from vCenter, and as you'll see, you'll add 2 additional NICs, one for the inside and one for the outside of the AVE on the edge side. So the architecture itself requires, of course, 3.1, vSphere vCenter 6, and host running 6 or later. The AVE service appliance requires 2 virtual CPUs, 4 GB of RAM, 8 GB of hard disk. It's actually very small. VM traffic via an inside trunk interface. East-west traffic is via the AVE. Any leaf traffic is going to go outside the trunk interface to the vNICs and to the leaf. And here's switch modes. So currently, this is what's available. No local switching mode. All traffic is sent to the leaf. Local switching mode, inter-EPG traffic that's entered to the AVE is sent to the leaf. And then a full switching mode is a future where intra and inter-EPG traffic are handled by the hypervisor. You can also have a distributed firewall. You can maintain security policies across VM moves. So in this case, AVE maintains a connection table that tracks TCP flows and creates a TCP flow table entry on receiving the first TCP sync packet. And you can actually view that right here. Sync and ACK attack from provider B to consumer A where connection is not initiated, fails since the packets are dropped by the AVE in the absence of a matching flow table entry. And here's additional distributed firewall implementations for the leaf and for the AVE. So here's some additional distributed firewall policies. You can configure vSwitch policies under the attachable entity profile. Under Create Firewall Policy, you can disable, enable, or learning. So let's actually real quick. Enabled is basically enables connection tracking in an AVS. There's a special mode called learning, whereas it basically creates the connections based on traffic, but it doesn't drop anything. So that would be useful during upgrades if you're not upgrading some non-supported release to a supported release and there's already existing traffic when the AVS wouldn't have had an opportunity to learn the flow. AVE use case would be a simplified UCS FI and blade deployments. So it would apply to any blade switch environment, though it doesn't matter. It overcomes configuration challenges in managing and scaling multiple VLANs with multiple UCS FI and blade switches. Trunking only happens on the infrastructure VLAN. There's also an investment protection use case. The AVE employs OpFlex to extend ACI to existing networks, so you can create a full layer 2 network and allow multiple hops between ACI and the hypervisor. Again, trunking only on the infra VLAN for all the OpFlex protocols. And then you can get visibility into virtual workloads. The AVE using no local switching mode allows visibility to all traffic. So again, you're talking about the black hole that exists between virtualization engineers and network engineers. Network engineers need to see traffic. Virtualization engineers doesn't really bother them if they don't see traffic. So the AVE use case gives you the visibility into virtual workloads, so I can see what's actually going on. Okay, the AVE uses no local switching mode, so it allows visibility to all traffic. It includes intra-EPG traffic. Monitoring tools do not have visibility in traffic locally switched by the hypervisor, so that's important for compliance for HIPAA and PCI. So here's an AVE use case for microsegmentation. Microsegmentation will automatically assign endpoints to logical security zones called microsegment EPGs. Microsegmentation with ACI supports virtual endpoints attached to the following: the ACI Virtual Edge, AVS, vSwitch, or Distributed Virtual Switch. The benefits of microsegmentation with Cisco ACI: all endpoints within an EPG can freely communicate by default. But what if an EPG contains a mix of production development servers, each required to communicate at different app servers or different layer 3 outs? Microsegmentation allows you to create microsegmentation EPGs and auto-assign endpoints based on various attributes. And you can also quarantine as well for a microsegmentation if there's a virtual machine that possibly has malware. Here's an example of microsegmentation within a single EPG. ACI can isolate traffic using VM tags for 2 VMs on the same port group in vCenter. You can see that each VM is assigned a unique tag. And here's an example of the microsegmented EPGs for dev and prod. So you can see that the microsegmentation attributes based upon their actual tag, Web 2 and Web 1. And the Web 2 dev contract is out OSPF, and the prod is going out the Web 2 prod contract under the BGP EPG. So here's where you can do east-west traffic based on VM attributes. You can create security across zones. So the user will create a base EPG in order to create a port group in vCenter. User creates an attribute-based EPG and associate it to one or more VMM domains. And a new encapsulation ID is allocated for this EPG with each associated VMM domain. The attribute-based EPG is not pushed to a new port group to the vCenter. If no matching policy rule is found in the APIC, the VMs will default back to base EPG level policy constructs. And here's a quick visual representation of AVE and virtual pods. So here you can actually have a virtual pod with the ACI policies. connected from a physical pod via an IP network using an VXLAN overlay to a virtual pod that actually operates with the AVE inside the hypervisor. So your use case would be colo facilities, brownfield, remote data centers, or bare metal clouds. Here's some virtual networking comparisons between DVS and AVE. And you can see the virtual networking comparison. OpFlex is running in the AVE, full layer 2 network, and distributed firewall. The AVE deployment steps: you download the AVE software from cisco.com, upload it to the vCenter content library, create the VLAN pool in APIC, create a new AVE VMM domain, use VXLAN encapsulation for microsegmentation, attach the ESX host to the new DVS for AVE, and deploy the API using the ACI plugin for vCenter. Now, this is a quick run through on NSX. I'm not that good on NSX. I'm going to be actually taking a class on it shortly, so I will get further information on that. But here's the NSX manager, manages all the components. Then the controller is the component that's required if VXLAN overlays with the unicast control plane. Then the ESXi kernel modules that exist on the hosts. The distributed logical router control virtual machines, and that's deployed in the edge image. And then the NSX edge services gateways, and they're deployed, that provides control plane and data plane for edge features for north-south switching. And VMware NSX recommended layer 3 routing design. Here's your fabric design. So you can actually see that it requires a leaf spine topology. It has to have sufficient bisectional bandwidth and redundancy. It assumes the network fabric serves only applications running on ESX hosts running NSX. So again, no Microsoft, no containers, no nothing, except for VMware. Integration with Microsoft. Here's the Microsoft Windows setups to integrate with ACI. 2 modes of operation. You can integrate with System Center Virtual Machine Manager or integrate with the Azure Pack. And here's the hypervisor integration flow. I'm not really going to run through this because there's just not that many people that run Microsoft. The Azure Pack Service Pack. The Azure Pack is a collection of Microsoft Azure technologies available to customers at no additional cost. Once installed, the Azure Pack integrates with System Center and Windows Server to provide a self-service portal for managing services such as websites, virtual machines, and Service Bus. It's a portal for admins to manage resource clouds, scalable web hosting, and more. So, of course, there is an ACI plugin for that. And here's the admin experience for the Azure Pack. You can add and configure service providers. You can do usage and billing. And there's your services this account has access to. Resources of ACI currently deployed. The application network profiles are created through the Azure Pack and pushed to the APIC using REST APIs. And here's the hypervisor integration process. You can pause and follow along. Integration with OpenStack. So OpenStack and ACI. OpenStack defines a flexible software architecture for creating cloud computing environments. The reference software-based implementation of OpenStack allows for multiple layer 2 transports, including VXLAN, GRE, and VXLAN. So this being Red Hat, you have the OpFlex for the Open vSwitch. That will extend the OpFlex agent from ACI into the Linux hypervisor. And the feature highlights is a fully distributed neutron network functions with NAT, integrated centrally managed overlay and underlying fabric, operational visibility with OpenStack, Linux, and APIC, and choice of virtual network or group-based policy-driven networking. Here's your OpenStack driver options. You can get the plugin from Neutron to the APIC policy model, or you can do group-based policy native drivers with interfaces directly with the APIC policy model. OpFlex extends ACI to the hypervisor. So the native neutron agent is using the Open vSwitch agent. So before OpFlex implementation, this is how it will work. But the OpFlex agent directly manages Open vSwitch and integrates with the APIC. And here's some key features of ACI integration with OpenStack. You can then map your OpenStack and ACI constructs, and also group policy objects. And ACI also provides support for containers as well for Kubernetes. Here's some Kubernetes VMM domain support. And Cisco ACI plus Contiv for Docker containers. So the Contiv master, Contiv APIC plugin. And some design considerations for endpoint discovery. Control plane learning is out-of-band handshake, vCenter APIs, in-band handshake, OpFlex-enabled host for AVS and Hyper-V or via LLDP CDP. Data path learning is for distributed switch learning. It's conversational, so as soon as I start talking, I'll be learned. The LLDP is used to resolve virtual host ID to attach port on the leaf node. Design considerations, hosts are assigned a VLAN ID to EPG binding through the VMM and APIC integration. Intermediate layer 2 nodes not managed need to manage VLANs on these for each VMM domain, and the endpoint location discovered through stitching. And for OpFlex base, the hosts are assigned a VNID and VSID to EPG binding through VMM and APIC integration. And here's the virtualization integration summary for each of these.